Good day, everyone. My name is Sharma, and first of all, I would like to thank Professor Carlos for giving me this opportunity to talk in this 11th scientific conference in applied physics at UFPES. The title I have chosen is like enhancing the heating efficiency by engineering the shape anisotropy in iron oxide magnetic nanoparticles. So this is the plan of my talk. First, I would like to discuss briefly the motivation behind this work. Then I will talk little bit about what is magnetic hyperthermia, what is spion superparamagnetic iron oxide nanoparticles, and the heating mechanism, how they dissipate heat when they are placed in a magnetic field. Then I will talk about magnetic vortex nanoparticle, is some special kind of magnetic nanoparticles where we have some vortex configuration, vortex states. Then I will talk about hematite and other iron oxide nanoparticles and stress, emphasize how to study how to produce vortex state and what is the role of shape anisotropy in heating efficiency. I will talk about synthesis and morphology also. Then a characterization about how we can characterize them so that to obtain one of the best specific observation rate. I will talk in that section. Then cytotoxicity evaluation against different cell lines. So if time permit, then I will talk about in detail about these cytotoxicity evaluation and then final conclusion. So the motivation behind this work is, as everyone know, cancer is one of the largest cause of death in developing countries. And if we talk about United States of America, 1 in 4 deaths is due to cancer. And in 2012, more than 40 million new cases and 8 million deaths were recorded. And it is estimated that by 2032, the number of cancer cases should reach 22 million. And if we talk about the annual expenditure for this cancer disease, according to 2010 data, it was approximately 1.16 trillion US dollar. And this is not a problem for developing country, but for every country we have similar problem. If we talk about Brazil, as per data available from Instituto Nacional de Câncer, São Paulo, in 2014 there were 190,000 new cases of the disease were registered in Brazil, and most of or majority of were from the cancer. So there is a huge challenge to tackle this disease and diagnose this disease and to find the way to treat this disease. And if we talk about the potential conventional treatment for cancer, the chemotherapy and radiotherapy are one of the best technique and routinely used nowadays. But they have severe side effects also, like burns, nausea, diarrhea, heart and vascular problems, and also most important, patient discomfort and weakness. So researchers are looking for new kind of therapy which is not very old and known as hyperthermia basically. And today's talk is basically localized heating hyperthermia using magnetic nanoparticle. So hyperthermia is a tumor treatment which uses thermal energy deposited to damage and kill cancer cells using coagulation necrosis in a living human body with minimum injury to normal tissue. So this is basically the substitute of radiotherapy and chemotherapy to reduce the effect of these this chemotherapy and radiotherapy. And if we talk about magnetic hyperthermia, so how we can use magnetic nanoparticle under the action of an AC magnetic field for heating above specific tissues from 41 to 46 degree for a few minutes in a controlled fashion. So you can see in the slides, you have cancer cells. So you have magnetic nanoparticle interacting with cancer cells. When they are placed in the magnetic field, there is complete destruction of the tumor cell. And this technique is a localized heating and is very interesting technique and substitute for chemotherapy and radiotherapy nowadays. And also it is multifunctional. So when we make magnetic nanoparticle, we can put drug, we can load drug, we can functionalize the surface of the nanoparticle, and also we can use these magnetic nanoparticle for magnetic resonance imaging contrast agent also. This is a recent example published in Nature Nanotechnology by some Korean group, where they have used exchange coupled magnetic nanoparticle for efficient heat induction. So you can see in this figure, you have untreated control sample. Then before treatment, you have core cell nanoparticle. Then you have Feridex, that iron oxide. Then you have DOX. So you can see after 18 days of treatment, there is a complete destruction of the cancer cell. So this is very efficient technique, and people are trying to increase the heating efficiency of a particular nanoparticle. But there are not so many nanoparticles that are approved and biocompatible. For example, in this work, they have used cobalt ferrites. So cobalt is toxic for the human being. The toxicity is high. So we have to think for nanoparticles which are biocompatible and less toxic. So if we talk about the necessary conditions for magnetic nanoparticle to use in hyperthermia application, first one, I should say that nanoparticle should be biocompatible and having low toxicity. And this is already approved by US FDA agency also, where iron oxide is routinely used as a contrast agent in magnetic resonance imaging, and also they are successfully tested for hyperthermia application in humans. Second thing is low remanence magnetization. So what is the advantage if we have low remanent magnetization in the magnetic nanoparticle? Then it have negligible dipolar interaction. This will help in avoiding the agglomeration and also to avoid the blockage when they are injected in the bloods basically. So this is and low remanent magnetization. If we talk about superparamagnetism, superparamagnetic nanoparticles or superparamagnetic iron oxide nanoparticles, they have low corrosivity, they have low retentivity or negligible, and this is one good example that spions are interesting for hyperthermia application, and they are thermally activated, showing relaxation, Neal and Brownian relaxation, and also they require low magnetic field to achieve saturation. If I talk about another condition which is prerequisite for these magnetic hyperthermal application, it is low saturation magnetic field. Generally, we cannot, when magnetic nanoparticle is placed in a magnetic field, we cannot apply a very high magnetic field and a very high frequency. So the product bit of field and frequency should be less than this, that is 5 into 10 to the power 9 ampere per meter second. And the last one is high efficiency. When we talk about efficiency, we are talking about the specific absorption rate and to minimize the dose for the treatment, and this can be measured and this can be represented by this equation, where this is basically the power absorbed per unit of mass of the nanoparticle. And how we measure this basically, so this equation is basically showing how we can calculate the specific absorption rate. So generally when we put magnetic nanoparticle in AAC magnetic field of suitable frequency and we record temperature versus temperature curve, and this is this slide is showing the profile between time and temperature, and from the slope of this curve we calculate the specific absorption rate, and where this is dt upon d small t, and here C is basically the specific heat of solvent plus nanoparticle, M prime is basically the mass of solvent plus nanoparticle, T is the temperature, small t is the time, and M is the mass of the nanoparticle. So this is the equation to quantify the SAR from the experiment, the standard calorimetric experiment. If we talk about the mechanism of loss of magnetic energy in the form of heat, there are three different mechanisms. One is susceptibility loss or Neal Brownian relaxation, Then we have viscosity losses, then we have hysteresis losses. So these three mechanisms are dominating when a magnetic nanoparticle is placed in an AC or in a magnetic field. So if we talk about susceptibility loss, then this is basically based upon a linear response theory where the specific observation rate is given the square of the magnetic field, and it depends directly on the susceptibility of the material and frequency. And where this susceptibility is given by this equation, where tau is basically the relaxation, the total relaxation, which is the sum of the Néel relaxation and Brownian relaxation. And if we talk about the viscosity losses, this is basically due to the friction between fluid and particle. And but in case of in vitro and in vivo application, these losses are very negligible and can be ignored. And third, hysteresis losses is basically the hysteresis losses, which is due to relaxation mechanism which are mainly blocked, and it happened in large particle or multi-domain particle. If we see super paramagnetic iron oxide particles, they don't display this effect due to the finite size effect. And the hysteresis, if they have the specific oscillation rate is generally given by equation A multiplied by F, where A is basically the area of the hysteresis curve and F is the applied frequency. So basically the hysteresis losses are more if area is more and if frequency is more. So but these type of effects are basically dominating in large particles or multi-domain particles. And if we compare superparamagnetism versus ferromagnetism, so we can say in case of superparamagnetism we have monodomains nanoparticles, we have no remanence, we have no coercivity, no dipole interaction, no agglomeration. However, if in case of ferromagnetism, we have multi-domain particles, we have larger hysteresis, larger remanence, more possibility of agglomeration, and you need very high magnetic field to saturate the sample. However, how to avoid these things, the large hysteresis loss, which is generally observed in multi-domain particles. So how to avoid this? So if we see the variation of coercivity be the diameter of the nanoparticle, the curves looks like as given in this slide. So we have different regimes basically. So we have super paramagnetic regime below single domain limit, and then we have blocked region, and we have the ferromagnetic region. But if you see in this slide yellow highlighted in yellow color, we have another region which is above the single domain limit, and where we have zero coercivity and zero retentivity, but also there is moderate hysteresis loss. And this regime is basically vortex regime, vortex state. I'm going to explain in the next slide. So here you can say if we compare superparamagnetism with the vortex. So we have in case of superparamagnetism, no remanence, no dipole interaction, no agglomeration effect. And in magnetic vortex, no magnetic pole, no remanence, but we have significant hysteresis. So, but question is how and how we can produce nanoparticle with vortex state. If we talk about vortex, what is the vortex state? So, in case of multi-domain particles, generally we have two types of domain wall. One is nil and one is block wall. And the magnetization vector is in plane in nil wall, where it is out of plane in block wall. And what happens when the diameter of the nanoparticles is reduced, and if when it is competing with the thickness, then what happens, that block wall is replaced by the nil wall. And in this situation, the two nil walls start intersecting each other, and this gives rise to the spinning of magnetic moment around a common core. And this state is basically known as the magnetic vortex state. And this state is some intermediate state, and the magnetic particles with a circular elliptical section, and is very important because this is dipole free configuration state, which is interesting not from hyperthermia point of view, but also to understand the basic physics also. And but about the strategy, how we can study these vortex state and how they are useful in hyperthermia application. We prepared some magnetic nanotubes, nanodiscs, and nanorings composed of iron oxide. This is the synthesis step, where you can see we have prepared some hematite nanoparticles using microwave hydrothermal synthesis. And it's very simple synthesis. We have taken iron chloride as a precursor, and then sodium phosphate and sodium sulfate as additives. And we found that by controlling the phosphate to sulfate ratio, we can tune the morphology of the nanoparticles. And this is an example where you can see when you are using low phosphate concentration of phosphate to sulfate, we have obtained nanotubes, hollow nanotubes. But when this ratio is high, we have nanoring sample. So generally, phosphate ion have very strong affinity for 110 planes and acts as a shape controller to induce anisotropy growth, while the sulfate ions with their weak adsorption affinity induce only the growth of polyhydra. And this is the growth process you can see. And we have optimized this synthesis, and this is the different morphology we obtained by tuning the phosphate to sulfate ratio, and also by changing the volume of the solvent, which is water in the present case, and also the temperature, the final temperature of the synthesis. So in this way we obtained different morphology. So here is, you can see the hematite nanoparticles we have capsule shaped microparticles, and we have ellipsoidal microparticle, and you can see also circular and spherical nanodisk depending on the phosphate to sulfate ratio. And we have observed that when the concentration of phosphate anion is decreased, as in case of figure D, and at the same time, if volume of the solvent is increased almost double in the present case, we have obtained a unique set of nanorings. Okay, so here you can see the these capsule shaped microparticles and how they are converted to nanorings basically. And if we compare the length of this capsule, it is reduced almost 10 times by changing the synthesis condition. And from X-ray diffraction, we have observed that these hematite nanoparticle consist of two crystallite size. First one is where you have majority of hematite with bigger crystallites and higher concentration. And another one is minority phase with smaller crystallite size with less concentration. And the concentration of minority phase is almost similar in all these capsule shape microparticle, ellipsoidal microparticles and nanodiscs, whereas it is only 5% in case of nanoring. And this is interesting thing is when we reduce the concentration of these phosphate ions, we obtain short nanotubes and long nanotubes hematites. And we have used these nanorings are thermally, these are thermally annealed in hydrogen environment to obtain iron oxide nanoparticles, magnetite or megamite something. And here you can see iron oxide nanoparticle after thermal reduction in hydrogen environment. So you can see nanorings here. Then you have, when you increase the concentration of phosphate anions, you have short nanotubes. Increasing it more, you have long nanotubes. So by tuning the phosphate anions concentration, we can tune the length of these hollow nanoparticles. And this is the XRD data, and here you can see after thermal reduction, we found that the nanoparticle consists of multiphase with mixture of hematite, magnetite and megamite. And if we calculated the percentage of hematite phase, and we found that in case of nanorings it was 3%, in case of single short nanotubes it is around 6%, and then 8% in case of long nanotubes, along with majority of phase of magnetite with minority of gamma iron oxide. This is FTIR analysis, and we have found the characteristic peak of iron oxide multiphase between 600 to 400 per centimeter. So, which identify that we have the mixture of iron oxide phase in these samples. To go more, we did Mossbauer spectroscopy because the phase composition is very important. So Mossbauer spectroscopy is done at room temperature for these nanorings, short nanotubes and long nanotubes. And you can see if we talk about hematite, so here the room temperature Mossbauer spectra is consist of 5 sextet, and the sextet corresponding to violet line is consist of hematite, and we have estimated the population of hematite, and it was around 7% for single short nanotubes, 8% for long nanotubes, which is very good agreement with the XRD analysis. And also it is also found from Mossbauer spectroscopy that the concentration of megamite phase is almost similar in all these 3 samples, and whereas the magnetite phase is approximately 78% in nanorings, 72% in short nanotubes, and 70% in long nanotubes. And some additional observation from Mossbauer spectroscopy is that the observed population of iron 3 positive cation residing on A site is about 3 to 4 times larger than those occupying the B site. And this indicates the presence of a large number of cation vacancies and defective region on B side. The results is a clear signature of formation of non-stoichiometry iron oxide, which can be represented by the chemical formula Fe3 minus sigma O4. And a higher fraction of iron 3 positive in A site arises from oxidation of iron 2 positive cations, a process that is enhanced upon increasing the concentration of the phosphate anion from nanorings to long nanotubes. And the observed relative composition of iron magnetite and megamite from Mossbauer spectroscopy analysis allow us to calculate the approximate value of magnetic saturation, which is very close to the saturation magnetization of the bulk material. And based upon the phase composition analysis, we propose a core cell morphology with the size which is very close that we observe from the structural analysis. This is the bulk magnetic property for these nanorings, short nanotubes and long nanotubes. Here you can see the MH curve at room temperature, and the observed saturation magnetization is very close to the bulk value, but if we compare with the value that we observed from Mossbauer spectroscopy, then there is some discrepancy, and which can be due to presence of some larger amount of non-stoichiometric iron oxide phase. And if we see the variation of corrosivity with the length of or thickness of these nanorings, short nanotubes and long nanotubes, we found that corrosivity increases with the increasing thickness or length of these nanorings or nanotubes, and which is due to the role of shape anisotropy. And the observed shape anisotropy were found to be approximately 2.1 into 10 power 3 arc per centimeter cube for nanorings, whereas for long nanotube it was 6.0 10 power 3 arc per centimeter cube. We have also simulated the hysteresis curve for nanorings and the long nanotubes, and the observed corrosivity is found to be very much similar. However, if you see, the interesting part is here there is a drop in the corrosivity from long nanotubes to nanorings, and also the presence of the vortex state. If you see in figure D3, you can see the nanorings as vortex state, which is in agreement with the previous published results for nanodiscs, whereas it is completely absent in long nanotubes, probably due to tabular morphology. You can see the different spin configuration as a function of hysteresis at different point. This is the magnetic heating profile. Basically, this is the SAR versus field at different at SAR versus field variation at some fixed frequency for these nanorings, short nanotubes, and long nanotubes. And we have found that the specific observation rate value is high for nanotube sample if we compare with nanoring samples, which is in contradiction with the previous results. So we have also plotted the shape anisotropy versus the SAR, and we found that this heating efficiency is enhanced exponentially from nanorings to long nanotubes at each field. There is exponential fit, well agreed with the experimental trend. And if we see the saturation magnetization for nanorings, it's larger than the long nanotubes. So SAR appears to be clearly dominated by the shape anisotropy, basically, in the present case. So in order to confirm this further, we unveil in more detail the role of shape anisotropy on the heating efficiency of hollow nanotube in comparison to nanorings. For this purpose, we have prepared another sample named here as capital S, where the length or thickness is around 300 nanometer, outer diameter is 207 nanometer, and inner diameter is about 125 nanometer, with corrosivity about 155 Oersted, which is very close to the corrosivity of nanorings. And the observed value of the SAR is about 409 watt per gram at maximum field of 450 Oersted, which is higher than the nanorings. Although sample S has lower saturation magnetization and similar corrosivity, the SAR value of sample S is higher than that of nanorings, which is a clear indication that better anisotropic property are translated into better heating profile. The observed results suggest that the contribution of the shape anisotropy is a key factor to enhance the heating efficiency of hollow nanostructure. To confirm, to go to more in to confirm or to go in more detail, we have confirmed this using dynamic hysteresis model, how the SAR value change with at clinically relevant condition for ferromagnetic iron oxide nanoparticle, and this model was proposed by Tong et al. Given by this equation, where mu naught is a magnetic permeability and k is a non-dimensional constant. However, we observed that the theoretical SAR value obtained through this proposed model, that is modified dynamic hysteresis model, does not satisfactorily reproduce the observed experimental trend. In fact, Tong et al. Has neglected the contribution from shape anisotropy in their work. So we modified this model and we put the aspect ratio into the consideration, and we modify the equation, and this is the modified equation, and these are the results. So here you can see SAR versus field for nanorings, short nanotubes, long nanotubes, and we can see here the prediction of SAR value using modified hysteresis model gives better prediction and very much comparable to our experimental findings. However, I want to emphasize here that we have not taken into account the nanoparticle size distribution, the coercivity, and the field alignment. To go in more detail, we have simulated the hysteresis for nanorings and long nanotubes in different direction of applied magnetic field. So these nanorings and long nanotubes are aligned in the presence of magnetic field at different angles. And here you can see a large hysteresis loss is found in parallel alignment for nanorings and long nanotubes. And such alignment results in highest SAR value. However, there is no significant differences in the hysteresis loss for both parallel and perpendicular direction of long nanotube, as shown in figure F. And if we see the recent reports, Liu et al. Has reported the highest SAR, approximately 3050 watt per gram per iron at 400 kilohertz and 740 Oersted for magnetic vortex iron oxide nanoparticle, which turned into a much lower value when analyzed at biological relevant condition. In another work by Das et al., the reported SAR value was found to be approximately 360 watt per gram at 800 Oersted. However, the experimental conditions used were far away from the biological limit. So, in brief, we can say that our long nanotubes, they are showing excellent SAR value under clinically relevant condition, and they are interesting for hyperthermia application, for in vivo hyperthermia application. And this is the cytotoxicity that we measured against three different cell lines: 41, CT26, and J774A.1. So you can see here the nano ring and long nanotube sample didn't produce any significant cytotoxicity effect for 41 and CT20 41 and J774A1 cells, whereas CT26 cells were found more sensitive when treated with both nanorings and long nanotube sample. And also we have observed that the viability reduction in CT26 cells followed a dose-dependent pattern, indicating the maximum concentration that should be used in this cell type during magnetic hyperthermia application. In brief, we can say the cytotoxicity experiment reinforced the possibility to implement long nanotube in thermal therapy based application. And finally, to conclude, we can say that higher SAR in iron oxide nanotubes is very important, and this is mainly due to the shape anisotropy, and this shape anisotropy is the main factor for higher SAR value and higher heating efficiency. I would like to thank my collaborators from Brazil, USA, Czech Republic, and from Doha for their help. And also I would like to thank my PhD student Gopal, who is working at University of Brasilia right now with Professor Coaquira. And also I would like to thank CNPq, FEPEMA, CBPF, CAPS, and NLANO for providing financial as well as other experimental support to pursue this work. And thank you everyone for your patience, and if you have any question, I'm happy to answer. Thank you all.